Back in 2017, one single research paper dropped that completely, and I mean completely, changed the game for artificial intelligence. It was called Attention is All You Need, and it gave us the transformer, the fundamental blueprint for pretty much every large language model we interact with today. So how did this one architecture spark such a revolution? Well, let's pull it apart and see what makes it tick.
Before the transformer came along, our models had a pretty big problem. They had to read text one word at a time, sequentially. Just imagine trying to understand a whole paragraph by looking at it through a tiny keyhole. It was slow, and you'd easily forget the beginning of the sentence by the time you got to the end. But the transformer? It just smashed that keyhole wide open. Its big breakthrough was processing the entire sentence all at once, letting every single word look at and connect with every other word. That's the magic of parallel processing.
So, here's our game plan for deconstructing this thing. We're going to start with why this was such a revolutionary idea. Then we'll look at the high-level blueprint, the encoder-decoder structure. After that, we'll dive into the encoder, then pop over to the decoder. And finally, we'll get to the secret sauce that makes it all work, the attention mechanism. All right, first up, let's really set the stage and talk about why this architecture was just so groundbreaking. I mean, look at the title of the paper, Attention is All You Need. The authors were not being subtle here. As this quote points out, they were making an incredibly bold statement right there on the cover page. They were basically saying, hey, forget all that other complicated stuff. We can build a top-tier model by going all in on this one powerful idea. Okay, so let's zoom out for a second and get that 30,000-foot view. We need to understand the basic blueprint of the transformer, which is this encoder-decoder structure. And here it is, the whole shebang. Now, I know this looks a little intense, right? But don't worry, it's really just two main components working together. You've got the encoder stack over on the left and the decoder stack over on the right. We're going to break this down piece by piece. The best way to think about this setup is with a classic task like translation. The encoder's job is to read and really understand the source language, like English. Then the decoder's job is to take all that understanding and generate the target language, maybe French, word by word. One side reads, the other side writes. So let's focus on the encoder. Its mission is to read the entire input sentence all at once. It chews on it and builds this really rich, dense numerical representation, basically a bunch of numbers that captures the full meaning, the nuance, and the context of that original sentence. And then the decoder gets to work. It takes that rich representation from the encoder and starts generating the new sentence, one word at a time. And here's the key. It's constantly looking back at what the encoder understood from the input, while also paying attention to the words it has already spit out itself. Okay, we've got the big picture. Now let's pop the hood and dive into the left side of that blueprint. Let's see what's happening inside the encoder. So inside each of these encoder blocks, there are really just two main parts. First, there's a self-attention layer. This is where the magic starts. It lets every single word in the sentence look at all the other words around it to figure out the context. After that, all that information gets passed through a pretty standard feed-forward network, which just does some extra number crunching to process it all a bit deeper. Great. Now, let's jump across to the right side of the diagram. The decoder looks pretty similar to the encoder, but it has one extra absolutely critical step. The decoder actually has 3 steps. It starts with its own self-attention layer, but this one is masked. All that means is it's not allowed to cheat by peeking at the future words it hasn't generated yet. Then comes the most important part, the cross-attention layer. This is the bridge. This is how the decoder pays attention to the output of the encoder. It ensures the translation is actually based on the original sentence. And finally, just like the encoder, it has a feed-forward network for some final processing. Okay, we've said the word attention about 1,000,000 times now. So let's finally get into the engine room and see how this thing actually works. This is the core concept. So, the big question is, how does a computer model, a bunch of code, actually pay attention to other words? What does that even mean? Well, it's done with a really elegant concept using 3 things for each word: a query, a key, and a value. The library analogy here is just perfect. Think of the query as the current word that's looking for some information. It compares itself to all the keys, which are like the labels on all the other words in the sentence, and when it finds a good match, a relevant key, it pulls the value,
which is the actual stuff, the meaning, inside that word's file cabinet.
And yeah, this is the famous formula from the paper. I know, it looks a little scary, but all it's really doing is calculating a score. It takes the query from one word and compares it to the keys of all the other words to see how well they match. Words that are super relevant get a high score. Then it uses those scores to create a new representation for the original word, blending in the meanings or the values of the most relevant words. That's it.
But it gets even cooler. The transformer doesn't just do this once. It uses something called multi-head attention. As you can see here, it's basically running that whole attention process multiple times, all in parallel. It's like looking at the sentence from 8 different perspectives all at the same time.
So why do that? Why have all these different heads? Well, this quote explains it perfectly. It gives the model more degrees of freedom. This is the real aha moment. Think about it. One head might learn to track how nouns relate to verbs, grammatical stuff. Another head might focus on conceptual relationships, like how king and queen are related. It allows the model to learn all these different kinds of associations all at once. It's incredibly powerful.
So let's put it all together. The big takeaways are these. The transformer was a massive shift from sequential to parallel processing. It uses this elegant encoder-decoder structure, which is perfect for tasks like translation. The encoder's whole job is to understand the input. The decoder's job is to generate the output, using that understanding through something called cross-attention. And the engine driving all of it is the attention mechanism, which uses queries, keys, and values to let words weigh the importance of each other.
The paper's title was Attention is All You Need. They proved it for language, and it started an absolute earthquake in AI. So I'll just leave you with this final thought. If attention is all you need for language, what else might it be all you need for?